We got to the point where we were talking about unit cells as being a small part of the structure which we need to be able to describe, and also within the unit cell there are even smaller bits which are called asymmetric units, and the asymmetric unit is then multiplied by the symmetry of the unit cell to give the full unit cell, and then the unit cell is repeated to give you the full structure. So what we're missing from our analysis so far, we've got all the intensities, we've measured all the intensities, we know the unit cell, we know the symmetry of the unit cell, but we don't know the fractional coordinates of the atoms in the cell. So what I'm going to be talking about today is how we find those fractional coordinates. And first of all, I'd like to point out that although Bragg's law describes the unit cell very well, where the reflections due to the unit cell will come, there are some deficiencies in terms of describing the full crystal structure. So the Bragg equation really imagines that atoms are sitting at lattice points and they're infinitely small, really. So it effectively gives you a grid. It describes a grid. It doesn't make any sort of compromise for... So basically, the Bragg equation deals with point atoms at the corner, at the intersection of these grids. Okay, so it's brilliant. It'll give you that in the cell. But what it assumes is that there's no atoms within the unit cell, and that the atoms points at the corner are infinitely small. They're scattered constantly all over. But that's not so. There are differences. First one I'd like to sort of draw your attention to is that atoms aren't infinitely small points. They don't scatter equally in all directions. If you scatter forward with an atom so that it goes directly forward, you'll find that the scattering power is equal to the number of electrons it's got. But as you go straight from the straightforward positions, i.e. theta is getting bigger, you go from the straight through position, you'll find that the intensity diminishes, the scattering intensity diminishes from an individual atom now. And the reason for that is that an atom is a ball of electrons, and it's the electrons that are scattering the X-rays, and they're not sort of a point electron, they're actually a little ball of electrons around the middle of the nucleus. And an electron here can interfere in its scattering with an electron in another part of the cell. So it's, if you want, a little cloud of electrons whizzing around. And if we get the wave scattered from this point here, it could cancel out from a wave or reinforce from a wave from a different point. So overall, the effect is to diminish the intensity. So as we go to higher angles, you'll find that if you look at a diffraction pattern, if you look at the one I recorded on film, or the one from the diffractometer upstairs, you'll find as you go to the edge of the pattern, as you go to higher theta, the intensity falls off because atoms have got a finite size, and the electrons within the atoms, they cause interference between the X-rays within that atom. So that's one difference. The second difference is that the atoms aren't sitting just at the corner of the unit cells. They're sitting all over the interior of the cell. And we've sort of made our calculation based on a wave bouncing off there, and there, and there, and there. We have said, well, what happens if it's scattered by that atom there, and there, and there, and there? So we haven't made that allowance. Now, fortunately, we can do it in the 2D. We can do it in the Bragg equation way. We can do it for the unit cell using the Bragg equation, and then deal with the interior of the cell afterwards. So the second difference is that we don't get this constant intensity due to all the diffraction being of perfect planes. There will be atoms scattered around the interior. And again, in the same way as the electrons in different points in the atom can give destructive interference and get a weaker intensity than you would anticipate from the summation of the waves, it's so inside the cell as well, depending on the position of the atom in the cell. When we get the diffraction of the Bragg planes, we could end up with the waves actually cancelling out. So you could have a very, very heavily scattering atom there, and another one there. And if they're in the wrong position, those two scattering events could cancel out and give you zero intensity. So if we sum up the contribution of all the atoms in the cell, although Bragg tells us we could have an intensity, it's up to the position of the atoms what sort of intensity we get. That's very, very fortunate. What I'm telling you is that the intensity depends on X, Y, and Z. Okay, so if the intensity depends on X, Y, and Z, we have now a key to try and retrieve X, Y, and Z. One neat little thing maybe I should point out to you is that the fractional distance between the planes is given by that term there. Hxj for atom J, Kyj, Lzj. And that's, although I myself find the definition of the Miller planes, Miller is a bit clumsy, 1 over H, 1 over K, 1 over L as the intercept. When you see it like that, it is rather neat that in order to find out the position, how far an atom is between the planes, which is what's important as far as interference is concerned, it's just this simple term, Hxj, Kyj, Lzj. And of course, if you get a different plane, the intensity will be different. It'll be dependent on H, K, and L. So you'll get that for each atom in a particular plane. And of course, if you sum it up over all planes and over all atoms, you get the full diffraction pattern then. And the phase change between the planes is given by this term. If that's a fractional distance, remember, in going from one plane to the next, effectively what Brown's law is telling us, there's a whole wavelength change in going from that plane to the next. That's why we can see it. So if that's the case, if we multiply that to 2 pi, we'll be saying that the wave is undergoing a phase change of 2 pi times the fraction in going from one plane to the next. And this gives us a way of summing up the intensities to give the correct intensity of the X-rays. So this is the grown-up Bragg equation, if you want. I prefer to use the bottom one. I can visualize it more easily. What it's actually describing is the summation of waves bouncing off the atoms between the planes. F is, if you remember, the intensity is given by F squared HKL, the corrected intensity. So F HKL is known as a structure factor. And there's one for each plane. Little f is the scattering from an atom. So Fj is the scattering from atom J. Remember, I just told you that Fj isn't a constant. It isn't just the number of electrons that atoms got. It will actually decline as we go to higher theta. But that is stored in the instrument, so we can calculate that very, very easily. And then HKL are the Miller indices of plane HKL. And Xj, Yj, Zj is the position of the atom in the cell in fractional coordinates. So what we're describing here is it's a wave, and a wave that's shifted depending on H times K, Xj, K times Yj, L times Zj, then times 2 pi. So the shift in the wave is given by that. So that's the scattering power. So if they weren't waves, all we have to do is add up the Fj's, and that would be the scattering power of the atoms in the cell. But because we're actually adding up waves being scattered by the atoms, we have to take into consideration the phase of the wave. I is the I of the square root of 1, of course. So this allows us to describe the phase of the sine wave that's been scattered by the atom. This is a pictorial representation of it. Okay, so all the waves will be the same wavelength, sorry, because we're dealing with the same HKL. And the shift is given by the position of the atoms, okay? So depending on the position of the atoms, that wave will be shifted along, back and forth. And then the intensity is given by the scattering power, little fj, of that atom. And basically, when we add all those up together, we end up with this wave here. We could have ended up with a lower intensity wave or no wave at all, depending on the phases of these waves here. Now, that's quite a complicated thing to envisage. So the standard way of doing that summation is vectorially. Remember, we want to give each wave 2 properties. We want to give it its amplitude, how big a scattering Fj is, but also we want to give it a phase. So a really, really neat way of doing that is to use a vector diagram like this. So the length of the vector is the scattering power of atom 1. The length of that vector is the catching power of atom 2, and the length of that vector is the catching power of atom 3. And the phase is given by the position of the atom. So this is given by hx1 plus kx1 plus lz1 times 2 pi. Okay, that's where that comes from. And then we can add them all together, and what we end up with is this vector here. So the sum of these three vectors is this longer vector here, the black wave there. So rather than trying to picture all these waves adding together, we can do it really, really neatly like that. And this is so neat, we use it in all kinds of other ways as well, because you've done bio-inorganic chemistry earlier in this year, in this academic year, and this would have been really, really useful then. This is what you would have used to determine the protein structure, and understanding of this would have helped you. So this gives you all kinds of information, but it's a really, really neat way of adding waves. And that equation I gave you is exactly that. Okay, so that's the pictorial representation of that equation. Now, possibly I should sort of point this out to you as well. The sum is that vector there. Now, what we measure using our X-ray diffractometer is that length. Remember, we're measuring f squared HPL. So I'm not actually measuring that as such, I'm just measuring the length. So I don't know whether the arrow's pointing there, or there, or there, or there, or there. All I know is its length from my X-ray measurements. And that does cause some important problems. Okay, so this is related to what we measure in the X-ray, but only the length of it. We can't actually measure this directly from X-ray. We can't know which way it points. There is a little bit of help at hand, though. If you've got a centrosymmetric structure, that is a structure where part of the symmetry is an inversion center, we will always have, anywhere we go above or below the plane, there will be an atom up in the same, relative to the plane, in the same position. That's what an inversion center does. Doesn't matter which way you go. So if we take the two hands, if you want, the two structures that we've got in the cell, and divide them into the two parts that are related by the inversion center, and build up the scattering of each atom underneath there. That's the same as I had on the other page. There's the first atom, there's the second, there's the third added together. But in this case, we've also got an inversion center, so we've got a second set of atoms which are below the plane. So when we send those up, the phase is going in the opposite direction, so we end up with that wave there. Remember, they're vectors. We don't have to add them in any particular order. I can add them in any order I want, vectors. So I've done it in this way because I want to emphasize something. Okay, so this is the summation, the same as I had over the page for a non-centrosymmetric structure. This is the additional part we have for a centrosymmetric structure. The important thing is, if we add now the sum of these with the sum of those, we go like that. So we go up and we go down. And effectively, what we do is we lose the sign term, okay? Effectively, the sign term, the I sign term that in one will be minus I sign in the other one. It'll be exactly the same magnitude, but opposite in sign, and they cancel out. Why is this a big help? Well, effectively, now there can only be two possibilities for the phase, okay? It can be pointing that way, or if we sum them up, we could have potentially had the arrow pointing that way. Okay, so we've only got two possibilities now. The phase can be 0, as I've drawn it there, pointing in that direction, or it could have been, not in this case, but depending on where the atoms are, we could have summed up and we could have ended up with the arrow pointing in the other direction. So rather than having any position around the clock for the phase of my wave now, it has to be, in a centrosymmetric structure, it has to be 0 or 180, plus or minus. Okay, there's only two possibilities. So that's quite a big help, because that's something we do, that information is something we need. Now, I know you're going to tell me that we can't get that information. If I asked you what the square root of 9 is, you would all tell me it's plus 3 or minus 3. I have no way of knowing whether you squared minus 3 or I squared plus 3. Okay, so the square root of 9 is either plus or minus 3. And that's the problem we've got. And why it's so important is that the equation I've just given you now is known as a Fourier transformation. It's actually a Fourier transformation of what's inside, the electrons inside the cell, the atoms inside the cell, if you want to. And any mathematician will tell you, if you've got a Fourier transform, there will always be mathematically a reverse Fourier transform. Okay, so if you can go one way, you can go the other way. So if you can go this way to give you the X-ray pattern, okay, Fourier transform the content of the cell to give you an X-ray diffraction pattern, you should be able to take the X-ray diffraction pattern and Fourier transform that to give you what's inside the cell. That's what the lens does, effectively, okay? So we want a program that does that. The big problem is this. This is the Fourier transform equation. That's the electron density at point X, Y, Z inside the cell. So you're building up the electron density in the cell, point by point. Okay, so little fractions by little fractions. So this would cover the whole cell, and you'd end up with electron density contour maps inside the cell. So if you had FHKL, and you apply this equation systematically, you would be easy peasy to build up a contour map of electron density in the cell. And where there's balls of electron density, that's your atoms, and that's the job done. The problem is this. We don't have that. We've got the modulus of HKL because we've got F squared HKL, so we can take the square root of that. So I can tell you what the modulus of HKL is, but I don't know what its phase is. Now, for a non-central symmetric structure, that could have a phase anywhere around the clock. For a central symmetric structure, that could be plus or minus, or it could be, in other words, it's 180 or not. So what's the problem? It's only plus or minus. Well, the problem is this. If I had a structure which I could represent by the summation of, say, 10 structure factors. Okay, so for each F, I would have a possibility of plus or minus. So for a 10 reflection structure, it would be 2 to the power of 10 possibilities. If I had 100 reflections, which I felt I could get a reasonable picture of the structure from, my strongest reflections, say, it would be 2 to the power of 100. So we can't guess this even for centrometric structures. We need some more help than that. And this was a big deal. Solving this was actually a Nobel Prize job. If you could figure that one out, because effectively it's what I've just told you. You've got the square root of 9 and it's plus or minus, and there's no way on mathematically of recovering that. Nobody's going to tell you, oh, it's plus or minus, because if you take the square root of 9, it's at either or. And this is the case here. But there's some physical things we can take into consideration. Okay, so that's a representation of what we want to achieve. Okay, that's the... If I could phase it correctly, that's what you would get. You would get an electron, and as you can see, it's very easy to find that there's 1, 2, 3, 4 atoms there. Okay, so the molecule I'm looking at is this. Okay, it's got 4 non-hydrogen atoms, and I can see the non-hydrogens really clearly there. So if I had the phasing there. Oh, this is another representation of it, by the way. Rather than put the phase in FHKL, I've given the modulus of HKL, and I've disembodied the phase, and I've put it in with the other part of the equation here. Okay, so in this way I've actually sort of separated the phase part out so that I can see what I need to. I've got this part already, but I need to get the phase part as well. If I could get the phase part, I get that nice electron density map, and that's problem solved. There's 2 ways of solving this problem. The oldest method is the heavy atom method. And basically, if you had a structure with a heavy atom in it, remember the vector, the size of the vector is proportional to how many electrons that are scattering in that atom. So if you had an iodine in your structure, that would have, I think it's 57 is it, electrons. So compared to say 6 for carbon, so it would be a really long vector like that. So if you think what happens in a structure now, I've given you an example here. There's the heavy atom, so all of the atoms are scattering, all the electrons that are scattering together to give us that nice long vector. And then this thing here I've pictured, which is meandering around, is all the other atoms adding together. Okay. Now what's likely to happen is that they're going to do something like that. They're not very likely to all gang up together and then start pointing down there to try and completely overturn the F heavy. So the chances are that if you've got a heavy atom in the structure, the phases of the total will be quite similar, because the rest of the structure, the lighter part of the structure, they tend not to gang up against it. I'm not saying it won't happen, but on the whole they don't. So that if you take the position of the heavy atom and using the first equation calculate the phase of the structure of that heavy atom, and then just give it to the modulus FHKL you've got, that's good enough. What you'll find is you'll get an electron density ball for your heavy atom, and you'll see the lighter atom starting to appear. And then you'll add that to it, and the phase will get better and better and better. So the oldest one is the heavy atom. So once you've got the heavy atom, the rest of the structure will actually appear. And what you've done in protein work is a relative of this. Okay, it's a relation of that. It's a more refined version of that. Now the problem is we don't know the position of the heavy atom straight off. So how do we do that? Well, remember, if we could apply, if we knew the phase of the X-ray scattering, we would be able to calculate an electron density map, no problem. But they didn't have it, okay? So this guy called Patterson, what he did was, he said, what would happen if instead of using F HKL, why don't we just use F squared HKL? You know, and do the same calculation, but use so we don't bother with the signs, we just use F squared HKL. And you do get a map, but it looks a bit like an electron density map. But it's not really an electron density map. What it is a map that's effectively, it's a convolution of every single position of the structure in the cell. And the way it manifests itself is that, imagine the structure transported with one atom placed in the origin, and then a vector drawn to every atom in the molecule. And then transports to the second atoms of the origin and do that again. And transports until the third atoms in the origin and do that again. So for example, if you had nitrate, for example, in an electron density map it would look like that. In a Patterson map it would look, I suppose there would be that element to it. You see one of those, but also you would see that, you would see that, you would see that, and you would see the vector between all the atoms transposed to the origin. So you'd have a chance, if your structure was just a nitrogen, you'd have a chance. But anything bigger than that, you would just be completely confused and you wouldn't get anything. Your only saving grace is that the intensity of these peaks in the Patterson is proportional to the scattering power of the two atoms at either end of that vector. Now, for example, if it was a carbon and a carbon, it would be 6 times 6. If it was an iodine and an iodine, it would be 50 times 50. So, in all that confusion, if the vectors between the heavy atoms would stand out like giant mountains amongst molehills. So you have a chance. Now, one very common example would be in a centrosymmetric structure, and the simplest centrosymmetric space group is P1 bar. Okay, so it's got two atoms in it, it's triclinic, and it's got X, Y, Z, and it's got minus X, minus Y, minus Z. That's all you've got in there. So the vector between two iodines in here would be X, Y, Z, minus X, Y, minus X, minus Y, minus Z. So you'd end up with a vector in the Patterson at 2X, 2Y. So that would be the vector between the two iodines in that structure. So, as I said, this is not that uncommon an example. There are quite a lot of structure are P1 bar. So if you had a structure where you had a bromine or an iodine in there, which isn't that difficult to do even in organic chemistry, you would be able to find the position of that heavy atom using that fairly simple method. Construct a partisan map, look for the most intense peak, find its X, Y, and Z position, halve them, and that's the true X, Y, Z position of that atom. It's fairly straightforward. Once you've got that, you can then substitute back in the first equation describing the structure to get the phase of the heavy atom, which can be made and used as the phase of the total structure factor. And very, very quickly you would gather the positions of all the rest of the atoms. So this was probably the method that a lot of people used maybe 30 or 40 years ago. So if you wanted a crystal structure, people would say, do I have to get an iodine or a bromine? That, thankfully, is long gone now, because we have a much, much better method of doing it. But that works and is very straightforward. The method that got its discovered as the Nobel Prize is known as direct methods. And it's a statistical method, so it's based on very, very simple relationships. And the important one is that if you looked at the contents of the unit cell, I gave you an example there, you will have balls of electron density and nothing. Okay, so if you looked at the unit cell in terms of electron density, to have negative electron density doesn't have a meaning. Okay, so a real unit cell will have balls of electron density and nothing. That's what it looks like. So does this actually constrain our structure, our phases? Yes, it does. Okay, so here's a very, very simple example here. So your decision is this. You picked maybe the 100 most intense reflections. They're good enough to produce you a very good electron density map of the structure. No problem, as long as you have their phases. So let's have a look at those reflections. 2 by 2 in this case. Okay, so if we've got that phase assigned to that reflection, you've got to make a decision now. Say it's a central symmetric structure. We've got a decision. It's either going to be this or it's going to be that. Okay, so the phase of the second wave can be in phase or out of phase. It can be 0, 180, plus, minus. That's the choice you've got. Is there something about those two possibilities that says, we're not going to use that? And I put it to you, there is. If we look at the minimum for this wave here, we find it actually coincides with about halfway up there. So it wouldn't be an extreme minimum. If we look at the minimum for this wave here, we find it actually coincides with the top of that wave there. And that's probably the most extreme point there. We've got that as slight negativity, and that goes below. So this gives you, if you want, the least extreme negativity. Now, I don't want negativity. I'm not talking about the charge of the electron. I'm talking about my electron density map having holes in it. And the reason I don't want that, because I picked the strongest reflections, and all the small reflections will actually give me more detail, but they won't fill excessive negative electron density holes up. Okay? So that's not too bad. If we now look at the other possibility where they're out of phase, we've ended up with the minimum of this wave coinciding more or less with the minimum of that. So we'll end up with a dip here which will take us down to about there. Now, that's not very likely. I'm not saying it'll never happen, but very unlikely to happen, because it's not going to be that easy to try and recover from that position. So what we're saying is that if we've got two intense reflections, and you only, for this purpose, you only work with the intense reflections. If you've got two intense reflections, you can then be fairly confident that the phase of the one with half the wavelength will be the same as the phase of the primary wave. Okay, so what has that done? In my example there, if I had 100 unphased reflections, I only had 99 now. Okay, that's not a bit lot. But in fact, what you do is you go through all the reflections and you produce a family tree of reflections being related to others. And in that way you whittle it down. So it's not a dramatic thing. The computer program will just sift through the reflections and find relationships between them and whittle it down. And normally what it does, it whittles it down to that every reflection is related to about 5 reflections in total. And it'll then just cycle through the faces of those 5 reflections until it gets something that looks like a nice peaky electron density map, and that's your structure. So that's what gets you a Nobel Prize, spotting that. Okay, so once they spotted that, then they could then build that, and it sort of more or less coincided with the advent of computers, and then people could then digitize this, and we never looked back, basically. So that's called direct methods. So once you've found some of the atoms in the unit cell, you can then produce a Fourier map or an electron density map, and then we can pick out the atoms in that. And when I say pick out the atoms, we get the fractional coordinates xj, yj, zj of the atoms within the unit cell. And if you've got those, now normally we wouldn't produce an electron density map. Okay, there's no reason for doing that. Computer is perfectly capable of picking up an electron density map and tell you that's where its middle is, that's where the atom is. So normally I wouldn't actually fish through that piece. I have done in the past, and I do occasionally now when I have problems, but normally you wouldn't need to do that. The computer will go through it and pick out all the atoms. And the first time I would actually look at it would be as a molecule on the screen, because the computer's picked out the atoms, and it's even smart on a computer. It's even picked out the heaviest atoms and called them chlorines or oxygens or whatever, and it usually does quite a good job. Okay, so I see a computer of the structure on the screen. What you do then is it will allow you to then to pick out any weaker peaks and so on, and add those as well from the atom list. So you do some work then as a crystallographer at that point. If the data is really, really good, you probably have to do very, very little work. So the thing is, like any experiment you do, nobody's going to believe you if you produce a nice picture of a molecule. Okay? So this is an experimental method. It is taken as absolute proof what the structure is. So we need to give people figures to prove this. And the way we do it is using a comparison of the measured X-ray intensity, which would be that modulus FHKL, and what we've calculated from the atomic positions. So if we're going to sort of get a good match, we could actually go through each reflection and say, oh look, that calculated HKL with my little xj's, yj, zj's really matches the observed one that I measured. Isn't that good? But then you realise you might have 100,000 reflections and it would get really boring. So what you do is you subtract the observed modulus, because remember we don't know its phase, from, again, the calculated modulus. We know that phase, but we want to subtract one from the other one. So f obs is the FHKL, which we've got from taking the square root of the measured and corrected X-ray intensities. F calc is the calculated structure factor we've obtained from the atomic positions. So if you subtract one from the other, we could then sum all those up. Well, actually, we can't sum up all those up as a good method, because if we summed all those up, some could be negative, some could be positive, and they could be an atrocious match, but as long as the negatives balance the positives, it will be good. So what you have to do is, you can subtract one from the other one and get a number, and then take the modulus of that as well. And then that would give you a measure of how good the agreement was. But you don't just stop it there, really, because remember we want to compare structures which have got 100 atoms in them with ones which have got 3 atoms in them, with ones that have got 1,000 atoms in them. So we want to compare all those. And each one of those structures will have a different number of reflections to describe it. So the small structure might only have 30 reflections, whereas the large structure might have 100,000 reflections. So clearly, if we just use that term there, it wouldn't be fair on the structure with a lot of reflections, because it's always going to be bigger than the one with 20 reflections or 30 reflections. So what you do to make it a fair comparison, you then divide by the sum of the f-obs. That normalizes it. And then what we have then is our R factor. So this is, if you want, the industry standard. So anybody who has a crystal structure done will say, my R factor is this. And what you're hoping you'll get is something that's about 3 or 4%, 0.03. 0.07 is fine. If it's higher than that, you have to explain to the referee at the publication, it's usually something to do with the structure having some properties that aren't conducive to give nice diffraction. Okay, so this is the industry standard here, the FOBS, which is what you've measured off your diffractometer, minus the FCalc, which you've calculated from your little XJs, YJs and ZJs. Take the modulus of that difference to get rid of the sign, sum it all up, and then divide by the sum of FOBS, and that will give you an R factor, which should be low, below 0.07, hopefully. It's common these days as well to weight the R factor, and when you see the figure with a W in front of something, what it means is, rather than just use the FOBS as they are, every reflection will have a standard deviation with it. Okay, that's from the counting statistics. So it is possible to weight reflections. So you'll see a weighted R factor, so that any reflections which are really weak can still be used, but they won't distort the structure too much. So that's the practice these days, to use weighted R factors, and it's very, very common not to use FOBS as such these days, but to use F squared. So you get F squared OBS minus F squared calc, and then the modulus of that. Okay, so there are a few R factors that are used these days. That's probably the oldest and the one people tend to refer to. But whichever one you use, they must be low for a good agreement. So now we've got an opportunity now to improve the structure. We've picked our X, Y's and Z's off our electron density map. Are they the best ones? Could we have picked one which is fractionally better? Well, now we have an opportunity to actually try and improve things, because if the R is a measure of how good the agreement is, if we, for example, adjusted X1 and made it bigger, a small amount, or smaller by a small amount, and then calculated the whole structure factors again and summed it all up and found that R was lower for one than the other, say, that's a better R factor. So we could do that for each X, J, Y, J, Z, J, and improve the structure. We don't do it in exactly that other way, but that's the basis of it. We can modify the XJs, YJs and ZJs to actually get a better R factor. It's the term we use. We can't be bothered to normalise it for the least squares process. So we don't have to bother to divide by for this purpose by the sum of the FOBS. And also we square it for the same purpose as I was taking the modulus before. Okay, so and hence it's known as least squares. Okay, so we take the modulus of the FOBS minus the FCalc as before, but this time rather than take the modulus of that, we square it. Okay, so that again we get rid of that sign. So whatever term we get, the summation of that should be at a minimum. Normal to weight them this time as well. So the weak reflections that are poorly resolved will be make a less contribution to our sum than the ones that are better defined and got a better standard deviation. But yeah, once again, this has to be minimized. And again, this can be done very, very straightforwardly these days. It's not done an atom at a time, you'll be glad to hear. It's done every single atom is adjusted at the same time using the inversion of a big matrix, a very large matrix. So every single parameter in your structure is adjusted at the same time. And this is repeated. It's the refinement is not a linear process, I should add. The equation is too complicated with that. So the refinement is an iterative process, and you could cycle several times, and gradually the structure, the Q will reduce and reduce and reduce until it reduces no more. And then, provided other criteria are met, that would be your final structure. And if that being the case, you would normally have an R factor of about 7% or lower, 0.07 or lower. And also, as part of this process, you would also have a standard deviation, a standard error for each of the parameters. So for each X, Y, and Z, we would have accuracy. And normally, that would amount to us getting bond lengths and angles with accuracy to the third, if not fourth, significant figure. Okay, so it's a highly accurate result we get from this least squares process. Least squares was applied in crystallography by a Manchester, somebody employed at UMIST, which is a foreigner at the University of Manchester. He was a professor of chemical physics, actually, but he wasn't a chemist, he was an engineer. So he's applying engineering principle very, very meticulously to our crystal structures, and this is the process that we still use today. It works very, very well, and if you want, it's an industry standard. So when we've got our final structure, it will be refined until all the bond lengths and angles are as good as you can get. In the initial stages, after the first phase of the refinement, we would actually be looking at the electron density. We wouldn't sort of just take that's the end of it, as other criteria have to be satisfied. And what we would be trying to satisfy is there is no further detail in the electron density map. So a fairly typical process would be to find the heavy atoms, as I had in that example I gave you there, refine those, and then create a difference Fourier map, and then look for the hydrogens and add those, and then refine those. And once all the fine detail had been taken out of the difference electron density map and these squares had converged, that would be then taken as the final refinement. So, as I said, in addition to getting an accurate X, Y, and Z for each atom, we would also have an estimated standard deviation is the old term for it. We also use standard error, standard uncertainties these days as well. So that's the newer term, SU. The older term is ESD. But what it means is that each parameter we derive using least squares will come automatically with an error because of the least squares process. So we will automatically have an accuracy for each bond length and angle so that you can compare structures. I can't leave it without mentioning vibrational parameters. And the reason for this is that it is part and parcel of refinement. It does seem a little bit strange we're using X-rays to determine the vibrations of atoms. But basically it goes back to how the scattering of the electrons. If you remember, they fell off with theta. Now what happens if the atom is vibrating, it will actually extend the little ball of electron density further. It will become more diffuse. And effectively, you'll find that the scattering will fall off even faster. So it is something that will have a visible effect on the diffraction pattern. And it's the reason, in fact, why we, as a matter of course these days, we pass a stream of dry nitrogen over our sample at a temperature of 100 K. Okay, so the cooling stops the atoms vibrating and gives us, not only reduces the sizes of the vibration, but also it gives us a better defined diffraction pattern to higher angles. Normally we wouldn't bother to refine hydrogens as anything more than isotropic. In fact, it's fairly common to fix them as a fixed sphere size. But it's typical and common to refine non-hydrogen atoms as anisotropic ellipsoids. And in order to refine something isotropically, obviously you just need one radius for a ball. It should find it vibrating the same in every direction. However, if you want to refine something anisotropically, you need 6 parameters. This isn't exactly a rugby ball. It's like a rugby ball, except it can be squashed in 3 directions. Okay, so it can be elongated or squashed in 3 directions, and so you need 3 terms for that, and you need 3 terms if you want for the tilt of the ball in the 3 directions as well. So you need, in order to describe an ellipsoid like that, you need 6 parameters. So for each atom in the structure, normally we would actually need 9 parameters for the anisotropic. So it's an X, Y, and Z, and 6 anisotropic parameters. And if we do manage to refine the hydrogens, we would need 4. Okay, so that's how we refine the structure. And this is a flow chart of how we do it. Okay, so this is the summation. I will sort of be referring to this at the end again. So and you'll see I sometimes ask exam questions on this sort of thing. But basically this is just a summation of what we've done now. So we came in with cell dimensions, space group symmetry, HKL and F list. So that's what we had to start off with. We then needed to phase the reflections, and that's known as solving the phase problem. Once you've got the phases, you can then go to a Fourier map initially, which would then allow you to pick out the electron density balls, the peaks, which would be displayed in a graphics editor, and you would have the opportunity, if you wanted to rename a carbon, a nitrogen, or whatever you wanted to do there. And then that would be handed on to the least squares process, where the atom positions and possibly the vibrations in later stages are refined. Then that would go back to the Fourier map, but then what you would get from this is normally a difference where you're looking what's left over. You would then go back to the graphics editor, which will show you the atoms, plus any additional peaks in the Fourier map. You would decide whether there were hydrogens or not, and then you keep going around until this process was finished. And at the end of that, you would produce your final result, which would be embodied in a crystallographic information file for publication. Homework, you can read the last bit of this now, it's not that exciting, okay, so it's just what happens at the end, so it's information we will get out. But I'll give you a homework, you can read that. It's very exciting.